In this video, I changed the shape of the population so that the population wouldn't be completely flat. So let's look back at the possible samples of 29 people out of 31. So here's this right here is the population of 31 people. Each person has a value. There's three people have threes, 3 people have twos, 6 people have each of these numbers, and 3 people have sixes, 3 people have sevens, and 1 person has an 8. These right here are the means of all of the different possible samples of 29 people that could be selected from this population. So if you select 29 numbers from here and you calculate the mean of those 29 numbers, you get one of these dots somewhere inside of here on the right side. So right here, this dot would be the mean of one possible sample of 29 people. So yeah, right here we have 29 people who have a mean of 4.2. Here we have 29 people who have a mean of 4. Here we have 29 people who have a mean of 4.1. So we have the population, the individual people, the sampling distribution, which is the means of all possible samples of the size that I'm selecting. Now there's also the idea of the standard error. The standard error is a value that measures how spread out the means of these possible samples are. So if I'm taking a sample of 29 people from this population, and I'm calculating the mean of my sample, if the means of the possible samples are really spread out over here, the standard error is high. If the means of the possible samples are closer together, then the standard error is low. So the standard error is basically the standard deviation of all of these different sample means in the sampling distribution. The standard error is just the standard deviation of the sampling distribution. And remember that the population mean, which is, let's see what the population mean is now, 4.12, which is right at the center of the population, is also the mean of the sampling distribution. It's also at the center of these possible samples. So if the standard error is low and the possible samples are all packed in close to the population mean right here, then what that means is that the standard error is low and most of the possible samples are pretty accurate. Most of the possible samples would give me a sample mean close to the population mean. But what if these possible samples are all spread out far away from each other, meaning some have really low sample means, some have really high sample means? Then the standard error is high, and most of the possible samples that I'm selecting from aren't very accurate. Most of the possible samples have sample means further away from the population mean if the standard error is high. So if I'm calculating the mean of a sample to estimate the mean of the population, I want the standard error to be low, because that means that most of the possible samples that I could get have sample means close to the population mean. They're packed in close to the population mean, and I'm likely to get a pretty accurate sample. I don't want the standard error to be high because that means that the possible samples have sample means that are spread out far away from the population mean, and I'm likely to get a sample mean that's not very accurate. I'm likely to get a sample mean further away from the population mean in that case. So low standard error means you're likely to have a more accurate sample mean. High standard error means you're likely to get a less accurate sample mean. If one thing that lowers the standard error is having a bigger sample size, is if you if I take a bigger sample from the population, then the possible samples will have sample means that are more packed in close to the population mean. So these are the means of the possible samples of 29. So these, so what if instead of taking a sample of 29, I'm taking a sample of 30? I'm taking 30 people from here, and I'm calculating the mean of my 30 people to estimate the mean of the population. Well, let's look at what the sampling distribution would look like. I'll replace this so it's the same population. So the population hasn't changed, but now these are the possible samples of 30 people that I could select because I just deleted one person from each column, which means that each of these columns is a different possible sample of 30 people that could be selected from the 31 people in this population that we see in column A. So let's make a graph of this sampling distribution of the means of all possible samples of 30 people. Okay, so now let's compare this to what we had before. So each of these dots is a different possible sample of 30 people that I could select. This is the mean of one group of 30 people. This is the mean of a different group of 30 people. These 30 people have a mean of 3.95. These 30 people have a mean of about 4.08. They're halfway between here. These 30 people have a mean of about 4.1. So let me do this so that we can look at it side by side. So here we go. This right here was the means of all possible samples of 30 people. These right here, oh, I'm sorry, these are the means of all possible samples of 29 people. These are the means of all possible samples of 30 people. And we can see over here that a lot of the possible samples of 29 people have a sample mean close to the population mean. All of these samples here in the center here are accurate samples that have a sample mean close to the population mean of 4.12. But down here we have some samples with sample means that underestimate by quite a bit. And up here, some samples with sample means that overestimate by quite a bit. Or at least under and overestimate more than the middle ones do. Over here, the same thing. We have some highly accurate samples in here in the center with sample means that are close to the population mean, and we have less accurate ones that underestimate down here, and some less accurate ones that overestimate over toward the right. But we can notice one thing about these two graphs. Over here, the means of the possible samples are a little bit more spread out, because here the samples have sample means spread out all the way between 3.9 and about 4.35. Over here, the sample means are spread out between 3.9 and 4.1. We don't have any sample means above 4.1 out here. So this is the highest sample mean that I could get. But over here, I might end up getting a sample mean all the way out at 3.8 I mean, over here, I might get a sample mean all the way out at 4.3 or a little bit higher. So these sample means right here are a little bit more spread out than these sample means over here. These are a little bit more spread out, and these are a little bit closer together, which means that overall, these sample means of 30 people are more accurate than these means of possible samples of 29 people, which means you would say that this sampling distribution of possible samples of 30 people has a lower standard error than this sampling distribution of possible samples of 29 people. This has the lower standard error because of less spread. This has the higher standard error because of more spread. And because this has the lower standard error, these larger samples are more accurate. And because this has the higher standard error, these smaller samples are less accurate. So one thing that makes the standard error smaller and makes the sampling samples more accurate is having a bigger sample size. If you take a bigger sample, then the possible samples that you could get from the population are closer together, and they more accurately estimate the population mean. But one other thing that makes the standard error smaller, besides having a bigger sample size, is having less spread in the population. If the population numbers are closer together and they have more similar values, then the means of the possible samples will also move in closer together. So if you're selecting a sample from a population that has low spread between the population numbers, meaning the population numbers are pretty similar, then the possible samples that you could get will be more accurate with a lower standard error. If the population has higher dispersion and the population numbers are spread out, then the possible samples that you could get are more spread out from each other, and overall they're less accurate. But if you're selecting a sample from a population with high dispersion, you can make up for it by using an even bigger sample size, because that bigger sample size will make up for it and make the samples more accurate. It'll make the possible samples that you could get more accurate, and you'll be more likely to get an accurate sample. So one thing that makes the standard error smaller and the possible samples more accurate is a bigger sample size. One other thing that makes the possible samples more accurate and gives you a lower standard error is having lower spread or lower dispersion between the population numbers. And obviously, you can't control how much dispersion there is in the population you're studying, so if the population has high spread, you just have to make up for it by using a bigger sample size. And there's formula that can actually be used to calculate the standard error. So what you would want to do, if you're calculating a sample mean to estimate the population mean, you would want to calculate your sample mean and calculate the standard error, because the standard error would tell you how far off from the population mean your sample mean is likely to be.